Hi everyone, today I'm going to introduce OpenCL. OpenCL, aka Open Computing Language, is an open royalty-free standard for cross-platform parallel programming of diverse accelerators. For parallel computing standard, we have lots of options. For example, on the CPU side, we have MPI, and on the GPU side, we have lots of graphics APIs such as Vulkan, DirectX, Meadow, and OpenGL. But these standards are only available to a single device type. While for OpenCL, the processors can be any mix of different types, including CPUs, GPUs, digital signal processors, FPGAs, and even tensor processors. So that is why OpenCL is often called the solution for heterogeneous parallel programming. The OpenCL framework contains two APIs. The first one is the platform layer API, and the second one is runtime API. The platform layer API enables a program to discover, select, and initialize compute devices. In parallel computing, we assign computational tasks to multiple processing elements to be performed at the same time. In OpenCL parlance, these tasks are called kernels. A kernel is a specially coded function that is intended to be executed by one or more OpenCL compliant devices. And the runtime API enables kernels to be compiled, loaded in parallel onto devices, and executed. The following example shows how OpenCL accomplishes task parallelism. I will also introduce some OpenCL concepts through this example. Assume we have three different tasks, foo, bar, and base, and we want them to be executed on different devices in parallel. First, the host application select devices, and these devices are managed by the host application through a container called context. Then, to create a kernel, the host application select a function from a kernel container called program. And next, the host application associates the kernel with argument data and dispatches it to a command queue. The command queue is the mechanism through which the host tells devices what to do. And when a kernel is in queue, the device will execute the corresponding function. To understand how to program OpenCL in more detail, let's consider three programming models: platform model, execution model, and memory model. These models interact and define OpenCL's essential operation. The platform model describes how OpenCL understands the compute resources in a system. The host is connected to one or more OpenCL compute devices, and each compute device is a collection of one or more compute units, where each compute unit is composed of one or more processing elements. Processors typically group processing elements into compute units for implementation efficiency through sharing memories, sharing instruction, dispatch, and also for increasing local interprocessor communication. And processing elements execute code with SIMD or SPMD parallelism. The next is execution model. In OpenCL, kernels are executed across a global domain of work items. The global dimensions define the range of computation. There's one work item per computation, and work items are executed on processing element, and also there's one work item per processing element. Work items are further grouped in local work groups for execution efficiency. The local dimensions define the size of the work group, and a work group is executed on a compute unit with sharing local memory and synchronization. But notice that synchronization between work items possible only within work groups, and global work groups are independent. So there is no global synchronization. So the items with gray color are not able to synchronize with items with yellow color within a compute device. For memory model, the OpenCL has a hierarchy of memory types. At the top is host memory, which is only available to host CPU, and global and const memory are available to all compute units within a compute device, and local memory are available to all processing elements within a compute unit, while the private memory is only available to a single processing element. OpenCL memory management is explicit, so these memory types, these memories are not automatically synchronized. That means the host application has to explicitly move data between memory types as needed. So OpenCL kernels are written in OpenCL C, which is a subset of C99 with language extensions for parallelism, with well-defined numerical accuracy and a rich set of built-in functions. Kernels can be ingested and compiled by OpenCL driver during execution. This is called online compilation. And they can also be pre-compiled into a binary format or spare V. This is called offline compilation. But unfortunately, offline compilation is not required by OpenCL standards, so it is optional, and it depends on vendor's implementation. And currently, for example, NVIDIA platform doesn't support spare V, so we have to use online compilation. And lastly, I will show you, I will give a demo to show you how to program OpenCL. And this demo is available at following repo URL. So basically, this program is really simple. It is just a program calculate vector addition, and OpenCL standard only provide C API, but the SDK of OpenCL managed by Kronos Group provides a convenient C++ bindings, just like Vulkan and So we are going to use the C++ bindings, and we start from the line 1. So by using C++ bindings, we have many advantages. For example, we can enable exceptions instead of classical C style error handling, and we can also utilize RAII to avoid manually free resources we allocated. So we enable exceptions by defining the macro CL HPP enable exceptions, and we also specify the version we are going to use, which is OpenCL 3. And the first thing we're gonna do is query for available platforms. So the platforms are stored in a std vector, and we call the static function get from the platform class. And we simply print some platform info to the standard output, including platform name, vendor, and version, as we can see in the first 3 line of the output. So on my computer, on my PC computer, I only have a NVIDIA graphics card, so we can see the platform name is NVIDIA CUDA, and it's from NVIDIA Corporation, and the version of this platform is OpenCL 3.0. And after get the available platform, we are going to query for available devices, and it's practically the same procedure. So we call the member function get devices from the object platform, and this parameter indicates we are going to query all type of devices, and this could be, if we go to the definition, we can see there are some other type of bit files, including CPU, GPU, default, accelerator, and custom. So, for example, we are going to use the all types, but since I only have one graphics card, so as we can see in the line 4 to 7, the information about we can see the information about the available device. So I have a GeForce GTX 1660 Ti, and it's from NVIDIA, and the version of the device is also OpenCL 3.0. And the third thing we're going to do is create a context. As I described before, the context is a container for device used by host application to manage devices. And since we only have one device here, so we just use the device as argument to create the context. And for simplicity, I use raw string to store the kernel source code. It for vector addition is pretty simple. So we just we have three parameters. The first two are incoming parameter are vector A and B, and the third parameter is the out parameter used to store the result. We use the built-in function get global ID to get the ID in dimension 0, since they are all 1D array. So this function call will give us the correct index we are going to use, and we simply add we add A to and B and store the result in C. So after creating context, we are going to build a program with kernel source code. And we know the program is a kernel container, so we just transfer the kernel source code to the program within context, and then we try to compile those source code by calling the build member function with some compilation parameters, compilation arguments. So we specify the version we are going to use to CL 3.0. And if the compilation failed, this member function will throw an exception. And in this case, we can further get build info, get build error from the program, and we just print the print the error messages to the standard C error. For example, if we just add some random chars to the source code to ruin the source code, sorry, this bug comes from C line, so maybe we need to recompile several times. So as we can see in the output, we can see we can get the compilation errors if the compilation failed. So next, after we compiled our program, we are able to select a function in program to create a kernel. We specify the kernel function parameters through template parameters, and we also specify the function name, which is corresponding to the function name in kernel source. And after that, we are going to create host buffers and device buffers. We first create host buffers via std vector, and then we create device buffers. So we simply transfer the data from host memory to device memory through the construction of buffer DA and DB. By using the iterator of std vector. And we also specify the third buffer DC to write only, since we only need to write the result to this buffer. We don't need to read anything from this buffer. And next, we create a command queue with context and device, and then we can enqueue our kernel with argument to command queue, so they can be executed on our selected device. So the sorry. So arguments contains the command queue we created, and also the global dimensions indicates the range of computation. So it should be the size. So it should be the vector size. So it should be equal to vector size, and we can also provide the local dimensions, which is the size of the work group, but we can left it default. So the C++ bindings will do the rest of things for us. And in C++ bindings, a kernel is a callable object, so we enqueue the kernels. We enqueue the kernels to command queue simply by call this object with argues and the buffer data. And in the end, we can copy the result from device buffer to host vector, and we check the calculation results. So since all the elements all elements in vector A is 1 and in vector B is 2. So the result should be 3, as shown in the command line. And all above code are enclosed in the try block. So if there's something wrong happened, we will catch the exception and print appropriate message to see error. And basically, this is a simple OpenCL program looks like. And thanks. Any questions?
I can ask a few questions. What platforms did you try this on? Were you working like mainly on Windows, or did you try to see if it works on Linux or Mac OS? I'm not sure.
I'm using Linux to program OpenCL. Although I'm using Mac OS to do the presentation, but this is a remote compilation. So I connect my Linux computer using via SSH. So and C-line support remote compilation. So this is all happen on the Linux machine.
Okay, I was just kind of wondering like how the support for OpenCL compares across different platforms, because sometimes some platforms have better support than others, but it sounds like Linux probably has pretty good support for OpenCL.
It depends on vendor's implementation. So for example, NVIDIA provides drivers for both Windows and Linux, but for Apple, they only support OpenCL 1.2 on Apple platforms, and for Intel they also provide drivers for both Windows and Linux. But as far as I know, the support for OpenCL is not as good as Vulkan, since although OpenCL is managed by Coronavirus, but the the group is mainly comes from Apple, and since Apple is going to develop their own graphics API method, also the compute API, so the OpenCL are not well developed since version 1.2, and the OpenCL version 2.0 is too complicated. It has many new features and are not easy to implement. So lots of vendors, including Intel, NVIDIA, and AMD, doesn't give a good support for OpenCL 2.0 for a long time. And the OpenCL 3.0, which we used in this demo, is just relaunched a few months ago. And as far as I know, Intel only NVIDIA gives programmers an easy way to install drivers, and for Intel and AMD, you have to build the runtime environment on your own. So you can imagine you can make lots of bugs and problems during this procedure. So from my point of view, OpenCL is not as good as other cross-platform general purpose GPU platforms, not standards like Vulkan, OpenGL, and other parallel programming standards such as OpenMP. So does that make sense?
Yeah. And you answered kind of the follow-on question I had, which was like, did you have to install special drivers for the NVIDIA support? And I guess the answer is basically for all the GPUs that you might be using, you need to install support. Because, for example, for some GPU support in Linux, you don't it kind of works out of the box without having to install drivers. But I find that like with NVIDIA, you always have to install like kernel. I don't know if it's kernel modules or like some kind of extensions in order to have support for it. But it sounds like maybe for OpenCL, no matter what platform you're using, it probably won't be supported out of the box based on what you're saying.
Yeah, OpenCL is not support out of box for almost every vendors. So you have to install something. And for NVIDIA, it's pretty convenient. So you just install the drivers. But for Intel, you can install drivers from apt. You have to download the source code and compile it and do many configurations and pretty complicated, and so it's not as convenient as NVIDIA.
Right. Maybe just one other question. I don't know if you know the answer to this or not, but would it be fair to say, like in this particular code example, probably that if you timed it, the bulk of the time is in the copying of the result, like copying data back and forth, rather than the actual vector addition? It might be an interesting thing to add into your demo. You don't need to add it right now, but just actually timing the part where it's doing the addition compared to the time when you're like copying data into the GPU hardware to do the computation and copying the result out at the end. Because my guess is probably the bulk of the time is in the copying, because the GPU is probably pretty fast at doing the addition. That would be my guess anyway. But
okay, I will add some benchmark after this presentation.
It might be an interesting thing to know, but yeah, that's all of my questions.
Okay, so I read some papers about the comparison between OpenCL, Vulkan, and CUDA. It seems like OpenCL is not really fast. Its advantages, its pros is not performance, but cross-platform and cross-processor types. So maybe CUDA and Vulkan is faster than OpenCL in this case.
Right. But for example, I guess if you had like a DSP, some kind of DSP coprocessor, you couldn't really use that with like OpenGL or Vulkan. But with OpenCL, it can support all kinds of computing devices, not just GPUs.
Yes, not only CPU and GPU, but other plenty of types of processors.
Okay, that makes sense. I don't want to monopolize the questions. Young-Soo, did you have any questions?
Does OpenCL provide some functions or parameters for synchronizing between parallel devices?
Yes, there are few built-in functions for OpenCLC, such as including some barriers and some other built-in functions, but I'm not post them in this presentation. But yes, there are lots of built-in functions in OpenCLC. So when you write kernels, so as I mentioned, there are synchronizations between work items. So within a work group, you can use those built-in functions to do synchronizations. So maybe, for example, imagine this is an image, and your algorithm will will possess the first row and then the second row and then the next row one by one. So maybe you can use the barriers to do the computation on the first row at first, and then you put a barrier. Sorry, maybe you can use some building functions to do synchronizations, and then the second rows and then the third rows, blah blah blah. So yes, the answer is yes. Yeah, there are lots of built-in functions to do synchronization. Does that make sense?
Oh yeah, sure. Thank you. Yeah, that's all.
Okay, then I guess if that's all the questions, thank you very much for your presentation, Diyu, especially since you're not feeling so well. It was a quite good presentation.
Okay, thank you guys.